Hi, everybody. Today we start a new chapter, chapter 17, and that chapter concerns the topic of electric potential, also known as voltage. So let's review some of the ideas that we had from the previous chapter. We talked about how if you have a test charge that was placed in an electric field, that charge will feel a force due to the field. And the equation that describes that is F equals QE, where F is the force, Q is the test charge, and E is the electric field. Now, this is a conservative force. And of course, what that means is that it doesn't pull energy out of the system, that energy is conserved inside the system if only conservative forces are acting on the object. So let's say that we have a test charge that's moved in the field by some external agent, and work is done by the field and the external agent. Then remember that the equation that we learned in first semester of physics for work for constant forces is work, W, is equal to FD cosine theta, where F is the constant force, D is the distance through which the object moves, and cosine of theta is the angle in between that force and the displacement that it moves through. So now that we've reminded ourselves of that equation, we can plug in the equation for F equals QE if there's a constant electric field into that equation for the force. So when we do that, we see that the work done by a constant electric field would be FD cosine of theta, where plugging in for F equals QE, you have QED cosine of theta, okay? Now in this case, theta would be the angle in between the displacement and the electric field, okay? Now, in your textbook, if you read through that, they go ahead and just set cosine of theta equal to 1, assuming that the angle in between the displacement and the field is 0 and not at some strange angle, okay? Now, remember, there's a relationship in between the work done by an external agent and the change in the potential energy of a system, okay? And that relationship is that for conservative forces, the work is equal to the negative change in the potential energy. W is equal to minus delta U, where U is potential energy. So now that we have the equation for the work done by the electric field, we can also write the equation for the change in the potential energy that that particle experiences when it moves through the field. And that would be delta U is equal to minus QED cosine of theta, okay? Yet again, delta U is the change in the potential energy, Q is the charge, E is the electric field, D is the magnitude of the displacement, and cosine of theta is the angle in between the displacement and the field. Now, yet again, this is a conservative force. The F equals QE is a conservative force. So what that means is that if only conservative forces are acting on the system, then the energies of the particles moving through these fields will be conserved, all right? So you have to ignore anything like air resistance or frictional drag or anything like that acting on the particle, and just assume that conservative forces only are acting. And then you can say that the initial energy of the system is equal to the final energy of the system because you only have conservative forces. Now, what that means is, remember our definition of mechanical energy is that and I understand here that we're using E for energy and E for fields, and I'm sorry for that. Let me see if I can make this a little bit more clear. Energy, there we go. I'm going to say energy. Too many E's, right? And then we'll do energy. Okay, there we go. Okay, that's better. So the initial energy has to equal to the final energy. So if the potential energy changes, remember that our mechanical energy is the sum of kinetic plus potential energy. The kinetic energy is the energy of the motion, and the potential energy is the energy associated with the conservative force, right? So here we have the change in the energy. If E initial equals E final, if the initial energy equals the final energy, then the delta energy would be 0. And then that delta energy would mean that it's the sum of the change in the kinetic and the potential energies, or delta U plus delta K for potential plus kinetic change, right? Now, what that means is that if the potential energy decreases, then the kinetic energy has to increase by that same amount, and vice versa, okay? That's what that means. Okay, so let's look at some scenarios here. All right, let's say that we have an electric field here pointing down, and the electric field is indicated by those orange arrows there. And then we have a particle Q naught the test charge particle, and it's moving in the field, and it starts at position A and undergoes a displacement straight down from A to B along the field line, okay? And the displacement D is indicated here on the graphic. So our equation for that situation, that exact same situation, is minus QED cosine of theta. Okay, now in this case, theta is 0 because D and E are parallel, okay, which means that cosine of 0 is 1. So you basically just got minus QED here that you're looking at. So what that says is that when it moves from A to B, that you're changing the potential energy for this positive charge, right? If Q naught is positive, then the change in the energy would be negative. It would be negative QED, right? All right. So that means that that particle, the charged field system, is going to lose potential energy when it moves from A to B. All right. So a system consisting of a positive charge and an electric field loses electric potential energy when the charge moves in the direction of the field. Another way to look at it is the electric field does work on the positive charge when the charge moves in the direction of the electric field. In other words, the acceleration vector from the F equals QE is going to point in the same direction of the field. And if that's the only thing working on it, then that would cause the particle to do, if anything, speed up, right? It's going to speed up. And so what that means is that the particle is going to gain kinetic energy if it's displaced in the direction that the field points and it's a positive charge. It's going to gain kinetic energy. And then that means, because the acceleration is pointing in the same direction as the displacement, it's going to increase speed, right? It's going to gain kinetic energy. And since delta energy is equal to 0, that means it has to lose potential energy, right? Because there's nowhere else for it to come from. So the potential energy is lost and kinetic energy is gained. And this is another example of conservation of energy. Now, let's say instead of a positive charge, now we have a negative test charge, okay? In that case, then your delta U is going to be positive because it's minus QED, right? The cosine theta is 1. It's minus QED if it goes from A to B. And then what that means is that Q is negative, and so that means your potential energy change is going to end up being positive because it's minus times a minus, right? So in that case, your potential energy is going to increase as it moves from A to B, which means that it's got to lose kinetic energy. And another way to think of it is for a negative test charge in this field, the acceleration would point opposite to the direction of the field, and then that would have a tendency to make it slow down. Remember that I'm talking about the acceleration. That comes from QE is equal to MA. So if the charge on Q is negative, then the acceleration is going to be opposite to the field, all right? And so that would cause a charge displaced from A to B, if anything, to slow down if there's nothing else acting on it. If kinetic energy, since kinetic energy is proportional to the speed, if the speed drops, then the kinetic energy also drops, which means the potential energy must be increased, okay? All right. Okay. Now you can see here that it's actually kind of annoying to have to consider the sign of the charge when you're looking at these scenarios, right? Like if you look at a charge moving through the electric field, F is equal to QE, and because the charge is inherently in that equation, which is related to the work and the potential energy, what happens to the potential energy is going to change depending on whether you have a positive or negative charge, and that's really super annoying. We would like to avoid that. So what we've done as physicists to get around that strange issue is to define what's called the electric potential or the voltage. Now, I find the fact that we call electric potential a different thing than electric potential energy, I find that kind of confusing. So most of the time, I'm going to refer to it as voltage instead of electric potential, just so it's clear that I'm talking about something that's not an energy, okay? Because the voltage is defined as the potential energy per unit charge, or U over Q naught, okay? When you divide out by that charge, what you're doing then is making the voltage a characteristic of the field only and not the charge in the field, right? So the potential energy characterizes the charge field system, but the electric potential or the voltage only characterizes the electric field. The voltage is independent of Q naught. And the voltage has a value at every point in the electric field. So we're going to go ahead and define it. We're going to use capital V, uppercase capital V to symbolize voltage here. And so voltage V is equal to the electric potential energy capital U divided by the charge Q naught. And yes, it's the same voltage that you see on batteries. Okay, so if you read off, for example, a C battery has 1.5 volts. Okay, and that's between the positive terminal, which has this little tip on it, and then the other side of the battery. And it's also oftentimes labeled plus and minus on either side of the battery to indicate which is the high voltage and which is the low voltage. So that's the voltage that I'm talking about here. It's the same thing. Voltage is a scalar, and it's a scalar because energy is a scalar. Remember, energy is a scalar, and so anything that's defined in terms of the energy with just constants multiplying or dividing will also be a scalar. Now, as a charged particle moves in an electric field, it's going to experience a change in the voltage. So remember that if your voltage is equal to U over Q, then what that means is that your voltage would be defined as minus EdQ cosine of theta divided by Q, which is minus ED cosine of theta, okay? And this is for constant electric fields, all right? So it's important to realize that for potential energies and for voltages, that it's really the difference in these quantities when they go through some kind of transition, the change in the voltage or the change in the electric potential energy, that's the meaningful quantity here. Not so much the raw number at some given point, but the change. Now, we often take the value of the voltage to be 0 at some convenient point in the field. And this point is called, oftentimes in electrical terminology, the ground. Okay, so that's the ground. Now, on that battery that I showed you a couple of slides ago, the ground is on the opposite side or the negative terminal of the battery. So we say that it's 0 on the bottom part of the battery and plus 1.5 volts on the top of the battery. Okay, so the ground is the back side. But that's not always where we define grounds. It depends upon the problem and the specific situation. In this way, it's kind of similar to how you define the 0 or reference point where you put your origin for those gravitational potential energy problems, right? Like, do you put your origin on top of the table or on the floor or at the top of the building or at the top of the tree? It depended on the problem, okay? And so it's the same kind of thing here. Now, voltage is a scalar characteristic of the field. It's independent of any charges that might be placed in the field, and that is super useful because now we can talk about the change of the voltage without worrying about what kind of charge it is. And like I said, I'm going to try and use voltage as much as possible instead of electric potential because I think it's confusing to say electric potential and then electric potential energy. That always messed me up when I was a student, so I'm going to try and help you out on that. Okay, let's talk units. So remember that we said that the voltage V was equal to U, which is the potential energy divided by Q. Now, the SI unit of energy is the joule, and the SI unit of charge is the coulomb. So we're going to define the SI unit of voltage as the volt, and 1 volt is 1 joule per coulomb. So that means that it takes 1 joule of work to move a 1 coulomb charge through a potential difference of 1 volt. Now, also, we can talk about how that's going to relate to the units of electric field. Remember a few slides back, let me show you that slide again, just so you don't get confused. We had the relationship in between the voltage and the electric field. There it is. Okay, so we said that the voltage is equal to minus the electric field times D times cosine of theta. Cosine of theta is dimensionless. Okay, so we have here the voltage is equal to the electric field times the displacement. So we could also define the electric field units in terms of the volt. And if we did that, it would be volts per meter. So previously we had used newtons per coulomb as the unit of the electric field. And now we can also say that that's equal to 1 volt per meter. So we can define our electric field as either newtons per coulombs or volts per meter. All right. So this indicates that we can interpret the electric field as a measure of the rate of the change with position of the voltage. Now, there's also a really interesting unit that gets used a lot in quantum physics and chemistry a lot, okay? And it's a unit of energy that's common in atomic and nuclear physics, and it's called the electron volt. And 1 electron volt is the energy that a charged field system gains or loses when a charge of 1 electron, which is 1.6 times 10 to the minus 19 coulombs. So remember that electrons and protons, that's how much charge they have, 1.6 times 10 to the minus 19 coulombs. And if a charge of plus E or minus E, an electron or a proton, is moved through a voltage difference of 1 volt, then that's 1 EV of energy, right? Because you have U is equal to QV. So the potential energy change U would be 1 electron volt when you have 1.6 times 10 to the minus 19 coulombs move through 1 volt, because it's 1.6 times 10 to the minus 19 coulombs times 1 volt. Okay, so 1 EV or 1 electron volt is 1.6 times 10 to the minus 19 joules. And that's a conversion that you'll see on the front and back covers of your textbook. So if you happen to see a problem where it gives the units of energy in electron volts, don't panic, that's what it means. And then this EV is symbolized, the electron volt energy, the notation for that, the abbreviation is a lowercase e followed by a capital V, and that's 1 electron volt. Okay, before we get into the example problem, I just wanted to remind you that constant electric fields like the ones that we're talking about today can be created by capacitors, which we're going to talk about in just a couple of lectures. So one really easy way to create a nice uniform straight electric field is to have what's called a parallel plate capacitor, which means that you have a positive metal plate parallel to a negative metal plate and separated by some distance we'll call D. Okay, so the plates have to be flat and uniform, and they have to be separated by that distance parallel all across the way, and then you'll get a nice uniform electric field between the plates. Okay, so let's say that we did that and we had a positive charge and it was released from rest, okay? So what would happen is, as we talked about last time, that charge would feel an acceleration in the direction of the electric field, right? So it would feel an acceleration in this graphic downwards. So it starts off at rest and then it's accelerated downwards towards the lower plate. Now we could figure it out, the motion of the charge using F equals ma equals QE and solve for things that way, but we could also use conservation of energy now to find its speed. And a lot of people really would rather do that because then they don't have to think about, you know, vectors and vector decomposition. So if this is the kind of problem that you have, then you can certainly do that. And that's because you're going to have a change in voltage, right? And that change in voltage will be negative for it as it moves along the field lines. You have higher voltages upstream on electric field lines than you have downstream. So you're going to have the high voltage up here near the positive plate, and you're going to have a lower voltage here near the negative plate. So if it moves downward, the voltage will drop, okay? And since the charge times the change in voltage gives you the electric potential energy, right? If you have a negative change of voltage and a positive charge, that means that you're going to have a negative potential energy change. And a negative potential energy change means a positive kinetic energy change. Because if energy is conserved, then you have delta U is equal to delta K. The change in the potential energy is equal to the change in the kinetic energy. Okay, so we're going to do an example problem about that in just a sec. So here's some of those equations that I put in words, okay? Now, if you're moving straight down the field lines, like we talked about in a previous slide. So in other words, if your displacement was straight from A to B, as it is here, which is in the same direction as the field lines, then cosine theta would be 1, and then you would have the change in voltage is just minus ED, okay? And then you could figure out the change in the potential energy, see here, by multiplying that times Q. So Q times delta V would give you delta U, and then delta U would be equal to minus delta K. All right, so let's do an example problem like that. We have an electron and it's moving parallel to the x-axis, and it has an initial speed of 3.7 times 10 to the 6th meters per second at the origin. And then that speed is reduced to 1.5 times 10 to the 5th meters per second at x equals to 2 centimeters. So calculate the potential difference or the voltage between the origin and that point, and which is at the higher potential or voltage. Okay, so I have drawn here a little x-axis for us, all right? You can assume that the tick marks here are in units of centimeters, and I've shown the position of the electron at time t is equal to 0, I guess, right here at the origin. It's an initial position. And then I've also shown that same electron, represented by that yellow circle, of course, at x equals to 2 centimeters. Now, the vectors here are the initial speed, or the initial velocity, which is 3.7 times 10 to the 6th. And then because the velocity is reduced at x equals to 2 centimeters, I represented that by a shorter arrow. Of course, these arrows aren't to scale. I'd have to make an arrow 1/10 the length of that, and I didn't want to go through all that. So these arrows are not to scale, but it is a smaller arrow for the velocity at x equals to 2 than it is at x equal to 0. So we have to use this information to calculate the potential difference or voltage between the origin and the point and figure out where the higher voltage is. So let's go through that. Okay, we're going to start with the fact that energy is conserved. Let me go ahead and put energy here. Oops, goodness, sorry. Just so it's not confusing, I'm going to say energy. Still. Okay, anyway, this is energy. Because energy is conserved, delta U plus delta K is equal to 0. So remember also that our change in the potential energy is Q delta V. That's our definition of voltage, okay? So we have delta U, which is equal to Q delta V, is equal to minus delta K, okay? And that comes from the fact that delta U plus delta K up here is 0, so delta U is equal to minus delta K. And then I plug that in for Q delta V. Now remember that delta K means the change in the kinetic energy, which is K final minus K initial. So we have minus K final minus K initial here. Now also remember from last semester that the kinetic energy for an object is 1/2 mv squared. That's the definition of kinetic energy, okay? So it said in the problem that this is an electron. We know the mass of an electron. We can look it up. It's in the covers of our textbook where it's very Googleable, okay? So the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So what we can do is plug in to our equation for delta K, okay, for this electron, and use that to figure out the change in the kinetic energy of that object. So we have 1/2 times 9.11 times 10 to the minus 31 kilograms, and then we're going to subtract or multiply that times the subtraction of the final speed squared minus the initial speed squared. So the final speed is 1.5 times 10 to the 5th meters per second. We square that and then subtract off 3.7 times 10 to the 6th meters per second, which is squared. When we multiply through by everything that appears in this equation, then we end up with an energy change of minus 6.2 times 10 to the minus 18 joules for the kinetic energy. Okay, that's how much the kinetic energy changed. Now, delta K is equal to minus delta U. So that means that the change in the potential energy is plus 6.2 times 10 to the minus 18 joules. Okay, and we know from the definition that links potential energy to voltage that delta U is Q delta V. So 6.2 times 10 to the minus 18 joules is equal to Q delta V. Charge on an electron is minus 1.6 times 10 to the minus 19 coulombs times delta V. So then to solve for delta V, we just divide through both sides by minus 1.6 times 10 to the minus 19, okay? And when I do that, I get minus 38.9 volts, and that's the change in voltage that that electron undergoes. Since the voltage change is negative, then that means that the voltage at the final position is higher, right, than it is at the initial position. I'm sorry, is lower than the voltage at the initial position, which means that the voltage is higher at the origin. I hope that's clear. Okay, so that answers all of the questions, I believe, from this question. It said to calculate the potential difference or voltage, to calculate the change between the origin and x equal to 2, and which was at the higher voltage. So we certainly did that. Okay, I hope that's clear. I hope it made sense. And I'll see you next time.